Hello everybody. In this video I am trying to cover few simple problems on series parallel resistors or combinations of series parallel resistances, and through these examples we are trying to see how we can apply simple laws for the analysis of electric circuits or networks. Alright, so let's begin with the first problem. Consider the network shown in figure below. Use Ohm's law, Kirchhoff's voltage law and Kirchhoff's current law to find Vx. This is the problem we have before us. Alright, so we will see how to do these problems. So if you look at these problems, they appear pretty simple. There is nothing so complex about it. So it is a simple logic, it's a simple understanding of series and parallel elements. If you look at this network carefully, it is so clear that this 16 ohm resistor, 5 ohm resistor, 4 ohm resistor, they are all in parallel. Alright, this parallel equivalent of 16, 5 and 4 when combined with 5 ohm series will offer some resistance to the source having a voltage of Vx, and correspondingly a current is driven out of the source. Now our objective is to find this Vx. What is this Vx? This is the question before us. What is Vx? How do we do? So it's simple that we somehow have to find out the voltage across this 5 ohm element and the voltage across these elements, these parallel elements, and we can add the two up, then we will get Vx. So we have a fair idea as to how to go about the problem. Alright, so we will start. How do we do? The solution goes this way. Solution is, we will find out the voltage here, the potential difference here. I will use the same green color. This potential difference we will try to find. Can we find the potential difference here? I will write it as V suffix 4 ohms. Okay, let that be the potential difference. Instead of marking it this way, I might as well mark it this way. This would be a better representation. Okay, so what is voltage across 4 ohm resistor? Because we know the current through that branch, we know the resistance, we can always find out what is this V 4 ohms. Voltage across 4 ohms is simply the current times the resistance, that is 7 into 4. This is 28 volt. Alright, so this 28 volt is the voltage across this 5 ohm also and this 16 ohm also, because 16, 5 and 4, they are in parallel. It is very clear. Alright, so now in order to get the potential difference across 5 ohm, that is here, this is V5 ohm, let me say this is V5 ohm, we have to find out the potential difference here. I need to know the current through this branch, only then I will be able to compute. So the question is, how much current is going to flow here? So in order to find out that, if I can somehow get the current in this branch, I can apply KCL at this junction, because I know this current of 7 amperes. I have found this current, that is I through 5, and this is I through 16. If I am able to get these independent currents, I will be able to get the current through this 5 ohm. And multiplying that with the 5 ohm resistance, I will be able to get the drop. So I know as to how to go about the problem now. Alright, so now we will try to write the things. We will try to, I want to remove only these things because they become quite cumbersome. This 5 ohm I will write it elsewhere. I will try to write this 5 ohm here, and this also I will write it a little neatly so that when you see this video you must be able to understand this very clearly. V through 5 ohms, if I want to get this potential difference, how do I do it? Okay, so I will call this current here, also as I'll call it as, let me call it as I1 because I've called I5 here. So let me not use the same thing. I will call this the current there. All right. So let's now go ahead. Okay. Having found this voltage of 28 volt across this 4 ohm, I can even get the current I5. I suffix 5 ohms is obviously equal to the voltage across 5 ohms, that is 28 divided by 5. I can calculate this. I will get the value to be equal to 5.6 amperes. Alright. Similarly, I will get the current through 6 ohm resistor, which again is 28 volt divided by 16 ohms. Alright. 28 volts divided by 16 ohms comes out to be 1.75 ampere. Alright. So from this network configuration, it is very clear that from KCL, these are all Ohm's law. These are all based on Ohm's law. Alright. Now we will try to apply KCL and see. Okay. From KCL, what we can write is the current I1 should be equal to, so the sum of the currents I6 plus I5 plus that 7 ampere. Alright. So we simply add the currents. Current entering the junction, if we call it as A, I1 is the current that is entering the junction or the node A, and I6, I5 and 7 amperes live out of A. So this is 7, this is 7. So 7 is here. Alright. Okay. Now this is equal to I6 we have found out to be 1.75 and I5 is 5.6 and this is 7. How much is this current equal to? This will come out to be 1.75. We need to compute this, plus 5.6 plus 7. This current comes out to be 14.35 ampere. Alright. So having found I1, we can find out the drop across this. This voltage or this potential difference can be computed. Okay, what is the potential difference? So I have indicated it as V across 5 ohms. I will now write V across 5 ohm is simply equal to I1 times 5 ohms. I1 we have found it to be 14.35 into 5. Okay, this 14.35 into 5 will come out to be 71.75. 70 volts. Now, if you look at this network, what is Vx now? Vx is simply V across 5 ohms plus this parallel voltage plus 28 volt. This is simply equal to how much is that? Plus 28 I have to do, right? So if I do plus 28, I will get this to be 99.75 volt. So therefore Vx is equal to 99.75 volt. Alright, it's a simple problem. It's a very, very simple problem. All we have to know is to understand the series parallel combination. Just to have a quick recap, what have we done? So we found out from the given data, we found out what is the potential difference that would occur across 4 ohm branch. That is what we did. That is 7 times 4, 28 volt would drop across for 4 ohms, which is in parallel 5 ohms and is in parallel with 16 ohms. So the potential difference across 5, potential difference across 16, potential difference across 4, all are 28 volts. Okay. So knowing the voltage, we computed the current I5, I6. It is simple. So we could find current I5 and I6. Alright. And these two magnitude, this computation was carried out using Ohm's law. Now, at this junction A, we were able to see that the sum of the currents entering should be equal to the sum of the currents leaving. There are 3 currents. One is the current of 7 ampere, the other of I5, the other of I6, I16, I could have called it I16. I do not know why I have taken it as I6. Anyway, it should have been 16, whether, okay, computation is properly done. Okay, so I5 and I6, I'm sorry, I'll correct it here. I'll correct this to be what? I'll make it 16. I'll make this 16. This is I16, and here also I'll do the same suffix 16. Okay, it shouldn't matter strictly speaking. Still, just to go with the notation, let's do it properly. I16 is 1.75, that is found to be 1.75. I through 5 is 5.6, and 7 amperes we've added, and we got it to be 14.35 amperes. So having found out this current, we were able to get the potential difference across 5 ohm to be 5 into 14.35, which comes out to be so many volts, and adding the two potential differences, I would get Vx to be 99.75 volt, and this would complete the problem. Okay, so let's see how we do a second problem. Here is another problem which we will take up. Simple examples I have taken so that series parallel things can be clearly understood. This understanding of these things are very important before we approach problems on mesh analysis, or for that matter nodal analysis. Alright, so in problem number 2 asks you to determine Ix in the circuit shown, I suffix x, right. So you can see the problem. So it's again a very simpler than the previous one. We have very few elements. There are 3 resistors and there is a current source. Okay, so how to determine the current Ix is the question. How do we do? What is our solution? So to get the current, you need to see how you can get this current Ix. Okay, so this source is letting out Ix magnitude of I suffix x magnitude of current through its terminals. So this current is Ix, which is the sum of the current that would go here and the current that would go here. Okay, so for our understanding, we will call this current I1 and I2. Okay, so for our objective is to first find out I1 and I2, then add the two, we will get Ix, that is a source current. It is as simple as that. So how to get I1 is the question now. So to get I1, we have the data, we have the potential difference across 3 ohm to be 24 volts, and from Ohm's law we can get what is I1. I1 is 24 divided by 3, 8 amperes. This is based on Ohm's law. Okay, this 8 amperes of current flows through 17 ohms also, because 17 and 3 ohm they are in series. Okay, therefore the potential difference across 17 ohms is equal to 17 into 8. Okay, it is very simple. 17 amperes of current, 17 ohms of resistance carrying 8 amperes of current will give us 136 volts potential difference. Okay, so what we mean is this potential difference is 136 volt. Okay, So this is my A, this is my B. Okay. Now, what is the potential difference across 19 ohm? Potential difference across, I'll use white pencil, potential difference across 19 ohms is simply 136 plus 24. This is 160 volt. Clear? It's like this. It is like this. The same network can be written in this manner, isn't it? Okay? We can even do this way. What I mean is, I can do this as 106. I'm sorry. How much is the resistance? The resistance is 17.3. This is 20 ohms. Okay, I've added the two resistances, 17 and 3, that is 20 ohms, and it is carrying a current of 8 amperes. So the potential difference can also be computed as 20 into 8, or else you can add, alternatively you can add 136 and 24. You will get 160 volts. Okay. So now, having found this potential difference, this is 160 volts, is also appearing across 19 ohms. This is 160 volts. This and this point, you get 160 volt. Alright. So the potential difference across 19 ohm is also 160 volts. So what is the current there through 19 ohms? We have designated that current as I2. So I2 is precisely 160 divided by 19. How much is that? 160 divided by 19 would make it 8.42 ampere. Okay. So that is the current there. Now it's simple. What is Ix? From KCL. See, from KCL, this is, we have called it as Ix equal to I1 plus I2. I1 is 8 ampere and this is 8.42 amperes. Alright, that comes out to be 16.42 ampere. This is Ix. Okay, that is the magnitude of the source now. Therefore, Ix equal to 16.42 amperes. Okay. So at every stage, we are using Ohm's law, and here we are using KVL, here we are using KCL, and everywhere else this is Ohm's law. So all we use here in these problems is simple elementary laws. Okay. This is another simple problem. There is one more. We will quickly go through the third one. This problem says, consider the following circuit. Which elements are in series? Which elements are in parallel? Apply basic laws to solve for Vx. So this problem is similar to what we have done previously. Okay, how do we do? We will try to, we are supposed to find Vx, right? So Vx obviously is the sum of the potential difference across 3 ohm, which we will for simplicity call this voltage. I'll use a different color. What I mean is, I'll use this green color. This is my V1. Okay. So I'll call this voltage at the potential difference to be V2, and let the potential difference here, let it be V3. I'll take this voltage plus V3. Okay, Vx is V1 plus V2 plus V3. Okay, it is as simple as that. So how to determine these voltages? See, across 12 ohm V3 is appearing, which is same as the voltage difference potential difference across 6 ohms. Okay, so to find out the potential difference, we need to know the current and the resistance. So it is very easy. V3 is equal to V3 is equal to 12 ohm voltage multiplied by its current, V equal to I into R. This is 6 volt. Okay, it's as simple as that. Okay, now what is the what do you say, how do we determine V1 and V2 now? It's simple. So V3 is the potential difference across 6 ohms also, the 6 ohms. So we try to find out that current. So I will call the current here, let me designate this current by the value, say I1. Okay, so I indicate something so that I can employ that as a that as an expression, or that quantity to indicate the current. Okay, so what I mean when I say I1, you obviously know I1 is the current through 6 ohms. That's why I have designated it as I1. Some designation you need to have. So how do we do? What is I1? Mathematically, I1 is from Ohm's law. It is V3, the potential difference across 6 ohms divided by 6 ohms. So V3 you have found out, 6 by 6. This is equal to 1 ampere. So I1 we have determined it to be 1 ampere. Okay. So at this particular junction, if we can call the junction, and let us say by some color as A, at A we can apply KCL now. What we have done here is Ohm's law. Now we will look at KCL at node A. At node A, what has to be true? I1 plus 0.5 ampere should be equal to this current. Which current? I will call this current, let us say, as I. I will call that current as I. This is equal to I. This is equal to current I. Okay. Okay, that's equal to current I. So what's current I now equal to? So I1 is 1 ampere, therefore I equal to 1.5 ampere. Okay, so you got this current. Okay, so knowing this current, we can get the voltage V1 and V2. Okay, so now if I is flowing there, what is the current through this? This has to be I, because the current at junction A splits into 0.5 amperes and I1, because it was 12 and 6 they are in parallel. The same two currents recombine at the node B or the junction B. So you have to have I is the current that returns from B. So same logic we use, and then now we determine V1 and V2. So what is V1 equal to? The voltage V1 is simply 3 into the current I, that is 1.5. This is 4.5 V. And what is V2 equal to? V2 equal to 2 into the current I, 1.5. This is 3 volt. Therefore our Vx is simply the sum of the 3 voltages. Vx, this is now we are applying KVL. This is KCL. Okay, what is Vx equal to? This end is positive, this is negative, positive, negative, positive, negative. So if I start from the source, I will come across positive negative drop, again positive negative drop, again positive negative drop. So everything gets added. So Vx equal to V1 plus V3 plus V2. V1 plus V3 plus V2. So V1 is 4.5, V3 is 6, V2 is 3. Okay, this comes out to be 13.5 volt. Therefore, Vx equal to 13.5 volt. Hence, the result. So, we are able to determine, what is needed for us. Okay. So, these are all simple problems which are basically check your understanding of KCL, KVL and series parallel. That is all, and Ohm's law, of course. Now, solve for the circuit. Last problem we will do quickly. Now that we have understood the first three, this is even more smaller and it is simple. We are supposed to find I12 and I6. How do we do? It's the simplest possible problem. Perhaps we could have taken this as the first problem. See if you can see across this particular current source. This is a current source. You have to identify very clearly that this is a current source which is living out 3 amperes through its terminals, and it will get back 3 amperes back to the terminal. Okay, this is what it means. The current 3 amperes comes to this point. I will call this junction or node as node A, this is node B. Okay, 3 amperes from the source comes to junction A or node A, and to come back to B, it has got 2 alternate paths. One, it can go via 6 ohms and it can go via 12 ohms, and those 2 currents we have indicated as I6 and I12 respectively, and the same 2 currents will recombine at B and it becomes 3 amperes and it gets back to the source. So, it is very clear that 12 ohms and 6 ohms are in parallel, and this 3 ampere current divides proportionately between the 2 resistances, that is 12 and 6. Through 6 ohms more current flows, through 12 ohms lesser current flows because of the opposition. So, we apply what we call as current division rule. Okay, it is a very simple current division rule. So, current division rule essentially deals with calculation of the branch currents between 2 parallel branches without computing the voltage. It is that simple. So, how do we do? So, current through 6 ohms, which we have designated as I6, is equal to the total current that comes out of the source multiplied by the resistance of the other parallel branch, that is 12, divided by sum of the 2 resistances. We do like this. Okay, it is very simple. It is a simple kind of a computation which is which gives you the current to be 2 amperes. Alright. So, if I6 is 2 amperes, what is I12? You need not apply now current division, because this we can apply KCL at the junction. I12 is 3 minus I6. So, this is 1 ampere. So, we have computed both the currents I12 and I6. Okay. Now, the question is, what is the voltage across the source? What is the voltage across the source? How do we determine the voltage across the source? It's as simple as that. It is voltage across the source Vx is nothing but the voltage across 12 ohms or the voltage across 6 ohms. Okay. So, that comes out to be either 6 into 2 or 12 into 1, and this is Vx equal to 12 volts. Okay. such elementary problems we need to do so as to understand these basic laws. Okay, you have done these problems in your first year, basic electrical engineering. Just before attempting elaborate problems, I thought let us have a quick look at some of the simple problems wherein we have different combinations of resistances in series and parallel, and you have voltage sources and current sources, how to compute the various parameters, various quantities in different parts of the circuit. Hope these examples are helpful in understanding these concepts. Okay, thank you. Let us see with more in the next video. Thank you once again.